here we're talking about exponential growth and decay. And the standard form of an exponential function is y equals a times b to the t, where a equals the initial value, and b equals the growth or the decay factor. Okay, and the dependent variable is represented by y, so what it equals, and the independent variable is represented by t, or what will be your exponent. Okay, so your growth and decay factor versus your growth and decay rate, because when you read these problems, you're going to be dealing with both. So if b is greater than 1, then b represents a growth factor. Okay. Note that b is equal to 1 plus r, where r is called a growth rate. Okay, so to say that again, if b is greater than 1, it's called your growth factor, when b is equal to 1 plus r, where r is called your growth rate. And we're going to look at that more in just a minute. Consequently, if b is less than 1, then b is known as a decay factor. Okay? And as an inverse to what we just said here, if when, and we're still talking about when b is less than 1, then we would say b equals 1 minus r, and in this case r is called a decay rate. Okay, and please note that the given growth or decay rate must be expressed as a decimal. Okay, so before we go on and talk about the example that is in your notes, remember that our equation that we're dealing with when we're dealing with exponential growth and decay, our original equation is this: y equals a times b to the t, where a is our initial value and b is our growth or decay factor. Okay, and we want our growth and decay factor, we need to express it as a decimal. Okay, well, I shouldn't say as a decimal, we convert our rate into, or our factor into a rate to express it as a decimal. So think about the example in your notes. I believe the example asks you for the decay, the equation for what it would represent. So if we look at it, you know your original equation would be y equals a times b to the t, and it tells you that your initial amount of time is 67.38. Then it gives you a decay rate of 2.6%. And you know, I told you here, your given growth or decay rate must be expressed as a decimal, so we're going to convert our percent to a decimal by moving it over 2 places, and our decimal becomes 0.026. Now, we want a decay factor in our problem, because b represents a decay factor, not a decay rate. Remember up here, this represented our initial value, and this represents a decay factor, or a growth factor. Okay, so you need to take your decay rate and convert it to a decay factor. Right up here, I showed you how to get a decay factor. 1 minus the decay rate. So our decay factor would be represented by 1 minus the decay rate. So our decay factor for this example is this. So for the first example in your notes, y is going to equal your initial value times our decay factor of 0.974 to the t, or to time in this matter. So we're going to put p, because that's what we're representing in your equation, equals this. So this equation is your answer for example 1. Okay? Then part B. It says in 1980, what would be your decay rate? Well, or what would be your population, I should say. Well, 1980 we could represent as your 0, because that's your starting point. So we could say P of 0, or P of year 0. So in this case, our T, or our time, we're going to put 0. So for the year 1980, we can say 0.974 raised to the 0 power, and of course we know anything to the 0 power is 1. So we can say 0.974 to 0 power, or 1, we'll go here, so we can say 67.38 times 1. We find out that in 1980 our population is still 67.38 because it hasn't decayed at all, because 1980 is our starting point. Okay, but then example C asks you, what about in 1986? Or what has happened in year 6? Well, keep in mind that this problem, we had a decay rate. So obviously after 6 years we have decayed. Had we had a growth factor, we would have grown. We would expect our number to grow. But in this problem we had a decay rate. So we're going to say P of 6 was the population in year 6 with the decay rate. So we're using our decay factor here to the 6th power. So we're going to do 0.974 to the 6th power. We're going to multiply it times our initial population, and we're going to come out with 57.53. And this makes sense because we should have been decreasing every year since 1986, or excuse me, since 1980. So logically, our population in 1986 is less than our population in 1980. Now, example D, I want you to work on your own, but it asks, what is it if it was a constant rate of decay? So in order to do that, you don't have to know how many years it's been, but you need to figure out exactly how much did it decrease each year, and what if it continued to decrease at that value over a certain amount of time. We can discuss this in class tomorrow.